Now let's talk about how to know if you're doing it right. I don't know if it has its own. When you use the extended Kalman filter, you have to supply a transition function and an observation function. Yeah. And in this case, they are those two neural networks that I trained for you and am giving to you. And they're encoded in the obs.json and trans.json files. Oh,
so you're supposed to use those as the...
Yeah, you will load those JSON files from disk into neural networks. And then those neural networks become the observation and transition functions that you will use for the Kalman filter.
Okay.
Or for the extended Kalman filter, rather. Yeah, pretty much the only implementation you're going to do is in this tutorial. Too far. Is that extended or is that the normal one? This is extended. You're going to implement these equations. And that's pretty much your job in this assignment. And remember, f is the transition function. So this is the neural network that you've got. And h is the observation function. So that's the other neural network that you've got. And let's see, capital H is the Jacobian of that transition function. So you need to know how to compute the Jacobian of a neural network, which we talked about in the last lecture. And let's see, where's the Jacobian of f? W is the Jacobian matrix of partial derivatives of f with respect to w. Yes. So w and h are your two Jacobian matrices. So you will need to write a function somewhere that takes as input a neural network and outputs a Jacobian matrix. In my opinion, the ideal place to put that would be in the neural net class. I could have supplied to you a neural net class that already has a compute Jacobian function, but if I did that, I feel like I'd pretty much be doing so much that you wouldn't get anything from the Kalman filter. So all neural networks out there in the wild provide a backpropagation operation, and so does mine. So I'm giving you that, and I'm telling you, using that backpropagation, you can write a compute Jacobian function. And if you do that, then you can compute W and H, capital H. And then after you've done that, then you'll also need linear algebra operations. So matrix multiply. Do I supply that in my code? Okay, so I'm really making this easy for you. Basically, just multiply some matrices together, do a little bit of linear algebra, and implement this cycle. And then recognize that the combination of x and p as they go through this cycle provide you the centroid and the size of those crosshairs that you're supposed to draw. So you draw the crosshairs on the screen and it follows the dot around.
So
is that
what's the difference between
high
the
level?
centroid and the dot? That's what isn't the dot the centroid already?
Oh, yes. Oh, no. Dot is the true state, the true hidden state. So the Kalman filter will never know where the dot is. The Kalman filter will only receive two parts of input. It will receive the observation, and it will know what actions you pressed on the keyboard. And just using those two things, it's supposed to figure out where the dot is and draw the crosshairs. No.
Generated by the transition model.
The latent representation of state generated by the transition model is right there.
Okay.
That's where the crosshairs is. So I could have just had you draw a dot, but I like crosshairs because they show both the position and the deviation.
Yeah. Okay, yeah, that makes sense.
So a better way to put it is these are not crosshairs. This is just a really it would be much better if you were to do a whole bunch of concentric circles with varying deviations. In fact, maybe we should do that instead of crosshairs. If you want to do that, that'll be fine. Sorry for changing the instructions on you as we go. But let us look at the normal distribution for a moment. This is the normal distribution. Mu is the center of the crosshairs. Sigma is one standard deviation away. Now, if we have a normal distribution, we know that 68% of probability 68% of the times when you draw a random value from this normal distribution, you will be within 1 standard deviation of the center, right? 95% of the time you'll be within 2 standard deviations. 99.7% of the time you'll be within 3 standard deviations, right? So if you will, here's how you know when you have nailed it, when you're doing your assignment correct. Let's suppose you draw your circle or your crosshair, the length of your crosshairs, to be 1 standard deviation away from the mean, from the centroid. Does that make sense? So if this is 1, and this is 2, and this is 3, then we can expect that if your Kalman filter is correctly implemented, then 68% of the time, the dot will be inside of the circle. So as you drive your dot around, the circle should be whatever size it needs to be such that you can get out of the circle about half of the time, but it catches back up, and you can't be out of the circle more than 42% of the time, because most of the time the circle is wrapped around you. And if you drew your circle 3 standard deviations away, meaning you'd be 3 times, your radius would be 3 times bigger than the 1 standard deviation, then you should never be able to drive that dot outside of the crosshairs, because assuming that this distribution is correct, assuming that its uncertainty correctly models its real uncertainty, then these percentages should match when it's right. Does that make any sense? So what I'm trying to get at is this is supposed to be a real distribution over its real confidence of where you really are at. And so if those percentages are about matching when it fits inside and outside of the circles, then you've nailed it. You've implemented a thing that actually understands not only what's going on, but it understands how wrong it is. So it has a knowledge of uncertainty. And that is quite a feat, because if you can pull that off, then you can feed this information into code for driving robots and flying Patriot missiles in to take out the North Korean nuclear missile that's trying to take out Guam. And you can, I don't know, I mean, in some respects, we're solving the problem of understanding true state based on observations. So is that not the same thing intelligence does when it looks at its world and says, I see, I understand, and that kind of a thing. So I don't know exactly how to tie the Kalman filter into AI yet, but I see this as touching on a lot of principles that are eventually going to all tie together in the grand AI scheme of things.
Does that generate your text?
Yes, mostly. So it is at this moment.
Yes.
When we call it x hat with a minus. X hat to the minus power sign. Why do you put a superscript minus? That's a weird notation in my opinion. But x hat minus is the output of the transition function.
Okay.
And then we correct it, at which point we just call it x hat. It's okay. When it's been first transitioned by f and then corrected by h, then we call it x hat.
Okay.
This is the observation that the Kalman filter receives. Yes, from the observation function with noise injected. Now, an interesting thing to do would be then to take its believed state and feed it back through the observation function. And what that would do is it would denoise the thing. You see what I'm getting at? Meaning, if you want to be awesome, you could add a second picture here, and that wouldn't be hard because the code's already there. Just copy the code and paste it. Instead of feeding so the noisy image was made by feeding the true state through the observation function to get a thing, and then injecting a bunch of noise into it. Then this is what the Kalman filter sees, and the Kalman filter computes its beliefs, which are its state that it understands. if you were to take its beliefs and feed it back through the observation function, you'd get a clean picture. Now the clean picture would be off a little because its beliefs are probably not exactly correct. So it might be moved a little bit wrong, but it will have no noise in it because it also doesn't believe it's going to see any noise. Or it doesn't believe there's noise in the real world. And so you could denoise all the images if you wanted. But for simplicity, I'm just having you draw crosshairs because it's easy. Yeah, so...
Oh, okay. I wasn't sure if it was just the raw data or...
To illustrate, true state goes through observation function to compute this image. Then noise is added. And optional, but would be really cool, is if you feed this through the observation function to generate another image, and then you've effectively removed all the noise from the observation. And this would be the, it's kind of like this is vision, and this is imagination. Because the imagination is the way you see the world in its rosy lack of complexity when you're dreaming at night. And it's just based on your belief state, not in any true evidence from the real world.
So the noise is supposed to model imperfect sensors, right?
Yeah. Okay. This noise is modeling imperfect sensors. Your transitioning noise is modeling imperfect actions.
Oh, imperfect actions, that's right.
Yeah. Or non-determinism in the world that's outside of your control, or something like that.
Both, right?
Yeah, both. And if you are feeling overwhelmed by complexity, it comes down to this. Code up these equations and try your darndest to think about what they mean. And when you connect them to these pictures, you'll start to see that this math computes how to do the pictures. If you can understand what the math means, that's really cool because that's awesome. I guess what a better professor would do is make you derive all the equations for the Kalman filter, but I've never done that, so not going to do it. Sound good? I think we've talked about some of the intuition of these equations, though. That's enough to satisfy me that they're valid equations and that Kalman, that if you study enough math, you can do things like that too. Okay. Let's see, something else I should mention. So the whole reason the Kalman filter uses covariance matrices is so that it can support notions of beliefs that are skewed and non-circular, right? When I inject noise, if you look at my code, you'll see what I do is I draw a random value from a Gaussian distribution and add it to the x-axis. Then I draw a random value from the Gaussian distribution and add it to the y-axis. That basically makes it a perfect circle. Do you see what that's all about? Okay.